melts at 300 degrees Celsius. It's the same, no change in the composition except it's a size. Right now, I'm talking about 2.5 nanometer size, which is very small. And you can see the dramatic reduction in the melting point. And again, the reason is melting means you have to move these atoms away from each other. You have to increase the bond length between the atoms. Now, if I have more atoms on the surface, then these surface atoms are linked to less number of neighboring atoms. So I need less energy for the surface atoms to move, right? And now when you go to the nanoscale, you have more and more atoms on the surface because it has a high surface area. So now since you have more atoms on the surface, I need lower and lower energy for them to move. And that's the melting ideally. And that's why you can see the melting point dramatically decreases when you go to the nanoscale. Another example is tensile strength. You see the stainless steel, which we think is one of the strongest metal. If you compare that with the carbon nanotubes, which are carbon nanoparticles, you can see a huge difference between the strength. And it's not only the strength, but now we know the carbon is very lightweight. So you get a very lightweight material, but a strength which is far better than a stainless steel. So these are some of the dramatic change in the property when you go to the nanoscale. Now the question is why nanomaterials shows unusual properties. I already tried to explain to you that one of the reason is high surface area. So why does the high surface area really matters? So if you look at any material, it has a one can divide that material into two things. One is a surface. Let us take this toffee. You have a surface and then you have a bulk. Now, what you see, most of the content of this material is in the bulk and only small portion is on the surface, right? So but interaction with a molecule or your own hand can only touch the surface, right? So this is another example. A coin, which has two surface layers and this 10,000 internal layers. If I reduce that, I cut that 2 mm coin into 1 mm and 1 mm, what happens? Now I have around 4 surface layers for this 10,000 internal layers. That means 2 surface layers for 5,000 layers, internal layers. That means I have now, by simply moving from 2 mm to 1 mm, I have increased the surface layers. But how much? From 2 to 4 doesn't really make a huge difference. But when you go to the nanoscale, then that could be dramatically different. For example, think about this cube, which is 1 centimeter by 1 centimeter. So the total surface area will be 6 centimeters square, 6 faces. Now, if I reduce or break down that cube from 1 centimeter by 1 centimeter size to 1 mm by 1 mm, right? Each of them are divided into very small cubes, and then you calculate the total surface area by calculating the surface area of each of these 1 mm cube. Then the total surface area is 60 centimeters square. So you increase from 6 to 60 when you reduce from 1 centimeter to 1 mm. Not dramatic change in the surface area. But now, if I reduce that 1 mm to 1 nanometer cubes, then see the increase in the surface area. 60 centimeters square to 60,000 centimeters square. So dramatic increase in the surface area. And that is the very first reason why these materials at nanoscale show dramatic properties. Because when I say I have high surface area, that means most of the atoms are now on the surface. And these atoms have a low coordination number because they have only few internal layers. So their coordination number is less. That means they have lots of unoccupied orbitals or dangling bonds which want to react with something. So they have high surface energy. And combination of high surface area, high surface energy, and most of the atoms on the surfaces makes these materials really reactive, and that changes their property. In addition to that, quantum conformant is another important thing that happens when you go to the nanoscale, where now when you make a bulk material, it's like you have taken the atoms and then made a molecules, and molecules become the materials. But now you're going back towards the atomic scale, and then the energy level splits, and that also helps you in tuning the properties of that nanoparticles. Okay, so I showed you what are the properties that changes, some of those, and I give you some brief reasoning why the properties of these nanomaterial changes. Now the question is, these nanoparticles are so small, how do I make them? How do I prepare them? That's called the synthesis or nanofabrication of the nanomaterial. So there are two main ways. One is called the top-down. As the cartoon shows, you have a gold ring in your finger, you take it out and break it until you get a nanoparticles. Now you will think, how can I break that big ring into a smaller nanoparticles? Obviously you cannot do it manually, but there are different instrumentation, laser, and other thing that allows you to break down the bulk into smaller nanoparticles. And that's why it's called the top down, because you already have a top size and then you are down, reducing it to a nanoscale. But this method doesn't really allow you to really tune the size, shapes, and other things of the material, so not really used regularly. Another method is called the bottom up. So what is at the bottom scale is atoms, right? So can I use the atoms and make the nanoparticles? Atoms or maybe molecules, and then you force these molecules and atom meet in certain directions or certain shape, and you get a nanoparticles of different sizes, different shapes, different morphology. And this is another technique where you start with some salt. Let us say if I have to make a gold nanoparticle, I start with a gold atom. If I don't have the gold atom, because you have to produce gold atom in the synthesis, so I take a gold salt, some salt, say gold chloride, reduce that into a gold atom, and I then create a scenario or create an experimental condition where say 100 atoms of gold meet to form a very small nanoparticle. If I need a bigger one, I make sure that 1000 atoms of gold meet and form a bigger nanoparticle. We can also tune how they meet. That way you can get a tubes, spheres, rectangles, whatever the shape that you need. The field is so improved now, progress now, matured now, that you can make different kinds of shapes in addition to the size tuning. Okay, so that's the bottom-up approach which is generally used. Another thing that you may now want to ask is, how do I see them? They are so small, smaller than the visible light wavelength, right? The way if things are small, we try to use a microscope and see it. But now microscope uses visible light. My nanoparticles are even smaller than the wavelength of the visible light. So I cannot use visible light microscope, but I have to still use a microscope. So in such a scenario, what I need a light which has a wavelength smaller than the nanoparticle. And there the concept of electron beam comes in. Consider a beam of electrons as your light source. And there the wavelength can be even in angstrom scale, sub-nanometer scale. And now using the electron beam, which is your light, you use a microscope and see the nanoparticle. And that's why the thing, it is known as electron microscopy, because I'm using electron beam in my microscope as a light source, and I see the nanoparticles. There are two ways. One is called the transmission electron microscopy, where you see how the electron is transmitted to your sample. That's why the name is transmission electron microscopy. And there is another technique called scanning electron microscopy, where you don't look at the transmitted electron, but you look at the reflected electrons or scattered electrons from the surface. So scanning electron microscopy gives you the information about the surface, whereas the transmission gives you the information of entire particle as a whole, right? And both the technique need to be used to get a real picture. So this is how the transmission electron microscopy looks like. Since it has electron beam, you don't want any gas molecule to come into its path. So your instrument need to be under a vacuum, so the electron beam goes straight forward and hit the sample, and you get a proper imaging. I'm just explaining in a very basic language. So that's the TEM looks like. These are the TEM images that you see now. You can see they have a triangle, a spherical particle. You have different kinds of hexagonal particles. Here, all particles are nearly spherical, monodisperse. You can even see the atoms. Now, the techniques of electron microscopy has improved such that you can see the atoms, distance between the atoms, so that I know now what is the distance between the two planes. And by knowing that D, I can find out what is the crystal structure of that material, right? So that's how you get the information about the crystal structure in the TEM. You don't need to even do the PXRD now. So this is a scanning electron microscope. Again, very similar way. It has an electron beam and a sample. Only thing is detector here detect the scattered electron or a secondary electron rather than the transmitted electron. And that's why you get information about the surface, the 3D information. So this is like a SEM of the copper oxide. You see these rods coming from the center, forming some sort of flower structure. This is another example of a TiO2 where the cubes are assembled to form some sort of a spherical particle. Okay, so that is all about the nanotechnology. Now I will change the gear and I will explain in a bit climate change. And then I will come back to the concept of nanotechnology and use our own research results that we're doing at TIAPA Mumbai and explain how one can use the concept of nanotechnology to combat climate change. So how do we understand the climate change? I think this one single slide helps you to understand the climate change. So we all know we are getting the energy from sun. So we're getting lots of energy from sun. All our energy is from the sun. While the sun rays come from the sun to planet Earth, some of them may get reflected by the environment, and majority of them pass through visible IR and some amount of 5% of UV light, and our Earth get heated. At the same time, our Earth's surface start reflect some, but it will start emitting some light. Secondary, we call it a secondary light, and that is in the form of infrared radiation. And this is a natural process. Some amount of the light comes in to planet Earth, majority of that get absorbed, and some amount get reflected or transmitted back to the space. And that's how you have a proper temperature that we need to have a life on planet Earth. Now, what happened?
There is some disturbance.
Oh, really? Maybe I will switch off my video then. Shall I switch off my video? Hello?
Hello, Dr. Vivek. There is slight disturbance.
Okay. Let me switch off my video and then maybe I will. Give me a minute. I'm trying to reopen my presentation again. Can you see my presentation now? Hello?
Yes, sir, we can see your presentation.
Okay. Where was I? Okay, here. So sorry for the trouble in between. I hope you are able to hear me now properly. So I was talking about So I was talking about the climate change and the main reason for the secondary emitted energy or light, which is in the form of infrared radiation, to stay within the environment of the planet Earth is carbon dioxide and several other greenhouse gases, mainly carbon dioxide. So carbon dioxide clouds or carbon dioxide in the environment now started capturing these infrared radiation and sending them back to the planet Earth, right? And that's how you have now more and more warming of the globe. So more the CO2, more amount of secondary infrared radiation will stay within the environment, and you will have our environment getting warm. So what is the simple solution then? The simple solution is somehow the excess CO2 that we have produced, which is 30,000 gigaton. If we can somehow find out a way to capture that excess CO2 from the environment, then you solve the problem. And that's what the aim of my talk, that at the end, after some slide, I will show you how one can use the nanotechnology to capture that CO2. And again, capturing of the CO2 will not solve the problem, right? I need to capture and do something with that CO2. So can I do something with that CO2 using the concept of nanotechnology? That is something I will come back to. But this is how the global warming or climate change can be explained. So in addition to the CO2, methane is another greenhouse gas, nitrous oxide. Water is also, but there is a debate because water is produced because of the global warming, right? If you reduce the temperature of the globe, water vapors will go down, but mainly one has to worry about CO2 to take care of the climate change. Why these molecules are greenhouse gases? Because they have an ability to absorb the infrared radiation, which is the secondary radiation that Earth is emitting when they absorb the sunlight. So any molecule which absorbs infrared radiation can by definition called a greenhouse gases, but you need to also think about the lifetime of these molecules. There are lots of molecules in organic chemistry that can absorb infrared radiation, but they are not in the environment, right? Their lifetime in the environment is really small. Whereas CO2 has a huge lifetime. It's very unstable, non-reactive molecule. And that's why it's one of the key greenhouse gas which is causing the climate change. So you can see here in this data, until 1950, the CO2 concentration in the environment in ppm was in the range. It was fluctuating, but it was always below 300. But suddenly at 1950, when real industrialization happens, you can see now there is a sharp increase in the carbon dioxide, and now it's around 450 ppm, which is again the history. It never happened in the lifetime of the planet, based on the data that NASA has. Now, since there is a more CO2 environment in the environment, those secondary radiation won't go out. You get more of them staying inside in the environment of the planet Earth, and what will happen then? The temperature of the globe increases. So you can see now temperature is increasing. But some people say, oh no, there could be that we are getting more sunlight. But if you look, the sunlight or sun energy that we're getting is nearly constant in last few years. But there is an increase in the temperature, clearly indicating the relation, a direct relationship of CO2 with the increase in the temperature. This cartoon tells you how the Arctic Sea is melting, right? You look at the y-axis, the millions kilometer. So in 1980, it was 7 million kilometer. Now you will see it's around 3.5 millions per kilometer in 2015. So 50% of the Arctic Sea is already melted. Now, if sea melts, the ice melts, what will happen? The sea levels will rise. It's not only because of the melting of the ice, but it's also because of the increase in the global temperature, right? So increase in the temperature will also increase the volume. Melting of the ice will also increase the total water, and sea level increases. And those cities which are really sitting at the sea levels will be under threat. So this is one of the recent recent paper in Nature Communication, very recent, 2019, where obviously it's a theoretical modeling, where they say that if we do nothing, this is our Mumbai, and this is what it will be in coming decade or something. So it's really a serious thing, and one has to really think about what we can do to stop the climate change. Not only the change in the temperature or the sea level, but the global warming also has an impact on the diseases that we are facing now. Because of the ice melting, NASA scientists have found several viruses and bacteria which are as old as 8 million years coming out, becoming live. And these bacteria are so unique that we don't have any molecular or any data, how they act, no data about that. No scientific data about that, and they are resistant to 18 types of antibody in this particular example. So you can imagine if we get infected by a virus or a bacteria which we have no information about, what will happen. Even COVID-19, we are really like stopped. Our life is stopped. But COVID-19, there were several coronavirus. So there was information about the coronavirus before, and that's how we were able to fight COVID-19 in terms of bringing the different medicines and treatments, possibly in next few months. Now the question is it too late to stop the climate change, or can we do something to stop the climate change? So I think there will be some people who say, oh no, this is how the nature works. So one day everything has to be extinct, and you can be happy. Okay, this is going to happen, so why to worry? Or you can be more scientific, more logical, and you say, no, I can protect the planet Earth. I can protect the nature. And this has to be done in a two way. One is a change in your lifetime, or societal participation, where you save the energy, you produce less amount of waste, you produce less amount of CO2, I efficiently use the energy, right? So these are the things that if we do, I think we will help the planet to protect itself. But by doing that alone will not solve the problem. There are lots of studies where they say, oh, as many trees as you plant, but it's not going to take care of the CO2 problem. Oh, that doesn't mean that you don't need to plant the CO2 trees, you must. But that alone will not solve the problem. So you need to have a scientific and research and a technology which will solve this problem. And that is CO2 capture and conversion. If we found a way where all the excess CO2 in the environment can be captured and then converted into something else, something useful, then the problem is solved, right? It's a very simple chemistry. CO2 plus water gives me, say, some fuel, right? I burn the fuel. I will show you this. Okay, maybe I skip this to save the time. So something like this. Right now, all of us is putting petrol and diesel to drive your car and bike and all the engines and everything. What about I put CO2 in my car? I fill my car with CO2. Now CO2 is not a fuel, so it will not burn. Then I have some sort of a catalytic reactor in my car which convert that CO2 into, say, methane or a methanol. So methane is a CNG. right? So methane is a good fuel, green fuel. So CO2 react with a catalyst, water, and a sunlight. Everything is free. CO2 is there in the environment, sunlight is there, water vapors are also there. So all of that gives me methane. Now I can drive my car or a bike or something, some engine by burning the methane. I burn the methane, I get energy. I drive the car, or I do the work, the engine does the work, and then methane gets converted into CO2. Now I will not let that CO2 go to the environment. I again capture that CO2 and again pass through the reactor, the catalytic reactor, and I get a methane again. You can see a cyclic process where no single molecule of CO2 is releasing into the environment. At the same time, it is becoming our friend now. It is helping us to drive the car. We don't need any petrol and diesel. And I will show you at the end of my talk that this is possible. At least the lab scale, this is possible. Obviously, at a commercial scale, one needs to have more fundamental discoveries, more fundamental research to really find out a good system so that you can do this in a sustainable and economical way. Okay, this is what my group is doing. We're trying to then develop, we're trying to find out this catalytic reactor, which allows me to capture the CO2, harvest the sunlight, capture the water, split it into hydrogen, CO2 plus hydrogen gives me the methane. A simple reaction, but one of the very challenging reaction because CO2 is a very linear molecule, very unreactive. So how do we do that in the lab? And that's where we go back to the concept of nanotechnology. Most of the material that you see are not that reactive that I can capture and convert the CO2. So in order to make the material reactive, you need to go to the nanoscale. Let us say I want to use the sand on your beaches. Can I use that sand and capture the CO2 and convert it into methane? It's not happening, right? You see, nothing is happening. But can I reduce the size of that sand to a nanoscale and see if that sand now starts behaving differently? Because we know when you go to the nanoscale, the property of the material changes. So I will show you how the sand can be made active and convert CO2 to methane. So this is how we design it. We take different bulk material or sometimes make the nanomaterial and try to capture the CO2, harvest the solar energy, and react CO2 plus water, which gives you the hydrogen, and you get a renewable fuel. So this is three component that you need. You need a support, you need active site, and you need a solar to hot electron. So now my talk will be a little bit technical because that's how I plan, some basics and some technical. So I already finished 30 minutes. So for another 30 minutes, I will explain you in more details about the work that we're doing. So the first thing is catalyst support, right? So what I need a catalyst which has the ability to capture the CO2, which has the ability to absorb the water from the environment, and has ability to harvest the solar energy, solar photons. And then I convert that photon somehow to the heat or electrons and inject that electrons to the CO2 or to the water molecule, get hydrogen from the water, CO2 plus water gives me the methane. Now, I want to use nanoparticle as a active site, because I told you that when you get a nanoscale, you have most of the atoms on the surface, so you get a extremely good reactivity. But the problem, the negative side of the nanomaterial is, since they are so small, so let us see if I start with a 5 nanometer gold particle, since they are so small, the 5 nanometer gold nanoparticle, rather than reacting with CO2, will react with another 5 nanometer gold, becomes 10, 20, 30. The particle size increases and activity of that material goes down, right? So you don't want these particles to meet. So what we do in our lab is then we take these 5 nanometer particle and fix on some surface so that they cannot move. So they remain at 5 nanometer across during the catalysis and after also catalysis. So what I need a surface, I need a support where I can put these active sites. Now it is very obvious that I need a surface which has a very high surface area. Higher the surface area, then I can put lots of these active sites, and that will allow us to develop a good catalyst. So how do I increase the surface area of the material? One is by reducing the size, which I don't want because I've reduced the size. Again, they will meet and center. Another one is by creating the pores. So we call it as a porous material, where pores is nothing but holes, let us say. So you have a sphere, create holes inside, and you get a porous silica. But porous silica has its own issues, because when you start coating your active site, you start blocking these pores. And ideally, you are losing this entire surface area. Even in this case, as soon as you coat these pores by the active site, you lose the internal surface area. So what we decided is to produce something like this, Nano Silica, which has this dendritic fiber structure, which will have a higher surface area and better accessibility. So this is the material that we have developed. This is our patented material, which is actually a silica, SiO2, a sand on the beaches, a purified sand, you can say, but in the form of a nanoscale, having a fibrous structure, and those fibers are dendritic. So that's why we call these other dendritic fibrous nanosilica. And one can tune the size from 50 nanometer to 200 nanometer. Again, you can get a 50 to 100, 100 to 200. You can get a different sizes. It has a huge surface area. Even the 500 meters per gram is like, if you take a 1 gram of a silica, you will have a 1 football ground in 1 silica, 1 gram of a silica. It's a huge surface area, which allows you to have then lots of active site loaded onto it. And even after that, the reactant can reach those active sites. It has excellent hydrothermal stability, mechanical stability, unique fibrous morphology, and it's easy to synthesize. Recently, we wrote this NACER protocol where you can use this. We also have given the video, so you can make this material in your lab. If you only need a round bottom flask, condenser, heater, and magnetic stirrer, nothing else, and you can make these materials that easily at a larger scales. So these are the SEM images, scanning electron microscopy images, indicating that these are highly monodispersed spheres, and when you go close, you start seeing those fibers. When I say fibers, these are not like a hairy fibers, but these more like a petals of the flower. These are the TEM images, again indicating the fibrous structure or fibrous morphology of these materials. And these are some of the more technical details about the endosorption behavior and pore size, which I will skip. Another thing that we try to understand in our lab is mechanism, formation mechanism. Why I form spheres? Why not a rectangular material? Or if it is a sphere, why it is a fibrous sphere? Why not a solid sphere? So this particular synthesis of DFNS is based on the templated mechanism where you use this molecule, which has this quaternary nitrogen and this long carbon chain, C16. So this is a hydrophobic tail, and you have this hydrophilic head. In the cartoon, it is shown like this. The blue sphere is a polar head, and this is a non-polar tail. Maybe I will show you the animation to understand this better rather than this cartoon. So you can see now. So these are the template molecules, a polar head and a non-polar tail. We added them into a solvent, xylene and water, mixture of xylene and water. Now you can imagine there will be repulsion between the hydrophobic and attraction between hydrophobic and hydrophilic. So in order to minimize the size, the total energy of the system, they self-assemble to form some sort of a laminar phase, which get further stabilized by adding these another co-surfactant molecule. And what we observe that these are not floating flat into the solvent, but they are in the form of a microemulsion droplets. And these droplets are the template molecules, or the reactors, you can say, which is made up of water, xylene, and that C-type molecule. Nothing. These are not a nanoparticle as such. These are the reactor where I can grow the nanoparticles. And in these channels, I can grow the silica. Now, we learn how to keep them away. If we keep them away from each other, I get a smaller DFNS nanoparticles. I can merge 3 of them, 4 of them, and I get a different sizes of the particle. In fact, I can merge all of them together, and I get a bigger droplet. And that allows me to then produce the DFNS of even bigger size. So that's how we learn how to make a nanoparticles of a different sizes as well as different fiber density. So our material is now being used by more than 150 groups worldwide for large number of applications: CO2 mitigation, drug delivery, sensors, battery, energy harvesting, catalysis, several different applications. Okay, so I'll explain you about the support. But these are the support. These are just a silica. Doesn't do much by itself, right? I told you the sand on the beaches doesn't do anything. So even you go back to a nanoscale size, still the silica is not active for CO2 activation. So I need to create some sort of active site. I need to put some other element on that silica to get me the catalyst. Now the example in the literature says that you take some metal nanoparticles, put it on the silica, and that will nicely convert CO2 to methane. CO2 hydrogenation. CO2 plus hydrogen gives me the methane. Methane is by CNG, green fuel. But the problem with these metal nanoparticles, in this case nickel, is they have a poor stability because they oxidize easily, and since they are very small, they also undergo sintering, and the catalytic activity decreases very dramatically. Now we wanted to solve this problem. How do I solve it? If I replace nickel by any other metal, it will be the same issue, right? Other metal will also undergo oxidation, also undergo sintering, and you will never be able to solve the problem if I keep changing the metals. Then we thought of, can I replace metal by something which has no metal, or can I just create a defects in the material, and can I see whether those defects can catalyze the reaction? And that's the new work that we did. We call it the metal-free catalysis, where silica alone can catalyze the reaction. The hypothesis was, I break this bond. Silica. This is a silica surface which is made up of SiO, just a siloxane. Now, if I break this SiO bond, what will happen? What will I get? I get Si radical and O radical, something like this here. I get Si radical and O radical. And then I ask the question that whether these radicals are active to activate the CO2, to dissociate the hydrogen, and force them to react. In fact, I can break this SiO bond also, and I get 2 Si radical and 1 oxygen vacancy. So these are the the defect centers that I can create. So by using the concept of so this is our work where we use this fancy word called perfecting imperfection, because generally we think imperfection is a bad thing, but in nanomaterials, imperfection is defects. If we can perfect them in terms of their proximity, their concentration, these defects can act as active site, and that's what we showed in our recent work. So we created the defect by treating the silica with magnesium, and we got different kinds of defects. We try to tune the defect concentration by playing with the magnesium concentration, 10%, 25, 50, so that we keep increasing the defect concentration. So you can see up to DNS 25, the silica still maintain its morphology, fibrous morphology, whereas at 50, the morphology is less and the surface area is less. And you can see when we expose these materials with UV light, they start emitting different colors, indicating now that they have a defect of different types which emits the light in different wavelengths. We did PL photoluminescence spectra to show that there are these defects for dioxosilane and silane, which concentration reduces when I treat that with a magnesium, 10%, 25, and 50%. Whereas another defect is formed at 600 to 1030 nanometer. These are broad because these are amorphous material, and these are for those O radicals, NBOAC size. And another center, the E centers. In order to see the E centers, we did the EPR, and where we observe that with increase in the Mg concentration, we observe that there is an increase in the E centers. When from 10 to 25 to 50, the concentration of E center is increasing. So 50 has the highest number of E centers. Using these preliminary data, we try to see whether these active site, these defect site, can do some catalytic conversion of the CO2. So this is a typical reactor. This is your reactor tube where we put this catalyst here. These lines are showing that these are the furnace where we're heating the catalyst at 400 degrees Celsius, 1 bar pressure. I mix CO2, hydrogen, mix them and pass through the reactor. So what will happen? CO2 plus hydrogen gives me methane plus water plus some amount of CO here, and this particular product outlet is connected to the GC, so you can monitor the reaction with time, and that's how we did. And you can see now DFNS, which is a pure silica, which also has some amount of naturally occurring defects, but as soon as we create more and more defects, you see now the methane yield, the CO2 to methane yield is increased, and you have 3750 micromole per gram of the yield. So I have another 20 minutes. We'll go a bit quicker. So what we learned here, that 25 has the highest amount of methane yield, and 50, which has more number of defect site, ideally has a lower amount of methane yield. So that question also needs to be answered, that why it is so. Another thing is about the stability. So with time, the stability goes down, not as bad as nickel, but still we thought of that there could be a carbon formation. So we heated them in air, and what do you see? You see at every cycle, the activity keep increasing up to 7th or 8th cycle, and now they become saturated here. So this is another question that we have to answer, is why the activity goes up. To answer two questions. One is why So what we observe that DNS10 has highest number of these O radicals, DNS50 has highest number of E centers, but somehow it's a DNS25 which is the best catalyst, indicating that you need both these sites nearby acting cooperatively to activate the CO2 to produce methane. So that's why we came up with the mechanism of cooperativity. Skip this. And by using the in situ diffuse reflectance IR infrared Fourier transform study, which is DIFT, we try to understand how CR2 interact with which defect site. Whether the CO2 interact with O radical, or silanols, or SI radical. And using this particular information that we gained from this experiment, we came up with this typical mechanism where we observe that CO2 gets activated by O radical as well as the silanol on the surface. You see here, silanol and O radicals to get the CO2 activation. H2 gets activated by the SI radical. You see here, SI radical, it dissociates the H2 into H, and another H goes to this carbonyl to form this p-carbonyl species. I'm skipping the detailed mechanism, but this is how we propose the mechanism based on the in situ IR studies. Okay, so that was the example where we created a sand to nano sand, ideally a silica to nano silica, and then created a defect by taking out some oxygen from that SiO2 to make it catalytically active. Only drawback of this particular process is this needs 400 degrees Celsius. So that makes the process unsustainable. So how do I now get a 400 degrees Celsius from sunlight? That was the next question. The energy required. Can I get that energy from sunlight? And that's the concept of our cold heating, where we need energy only at the active site. Not entire reactor doesn't need to be heated at 400 degrees Celsius. So can I only heat the active site, that defect site at 400? We're keeping entire reactor at room temperature. That's why the concept of cold heating. And this can again be done by the gold. I told you that gold nanoparticle oscillate, the electron cloud of the gold nanoparticle oscillate with the wavelength of the light, and at one particular wavelength there is a resonance called surface plasmon resonance. And when this get damped, the energy get damped in the form of a heat, as well as some of the electrons in the Fermi level goes to the excited state, and we call them energetic electrons or hot electrons. So can I use these hot electrons and this thermal heat to catalyze the CO2 conversion reaction? So this is what we did in our recent work. Since I don't have much time, so I will quickly explain this here. So what we did, rather than playing with the size of the gold nanoparticle, we decided to tune the distances between the gold nanoparticles. You see DFN sphere, and then each of those fibers were decorated with these gold nanoparticle, and we kept bringing them near and near, closer and closer, so that the electron cloud of the two gold nanoparticles start coupling with each other. And then there is something called the surface plasmon, the plasmonic coupling, which affects the surface plasmon resonance, and you get a broadband light absorption. Now you can see these are the electromagnetic the EM imaging, where you can see now with increase in the cycles of gold loading, the gold nanoparticles are coming closer and closer and started connecting with each other, and that's what we wanted. And what you see here, skip this. What you see here is that with gold nanoparticle coming together, the color of the gold changing, and now you can make a black gold, a gold which is black in color. No doping, no oxidation, nothing. It's only change in the particle size and the distances between them, which makes them gold black. So when I say black, you cannot say I have a black carbon, but this black color is because of the light absorption, right? So that means you are able to harvest maximum amount of sunlight. You can see here a broadband absorption. You absorb visible light, even the near IR light. So whatever the light you get from the sun, you are harvesting that, and you will be able to convert that either into heat or the electrons, hot electrons. And the heat that is produced by exposing the black gold with sunlight can be used to convert the seawater into drinkable water. You can see we can evaporate the seawater by just putting the black gold and light, and capture the vapors, cool it down, you get a pure water. You may say that why do I use a black gold, which is expensive? True, but this is catalytic. You don't need large amount of black gold. And you can reuse the black gold. So ideally that will make the process ideally sustainable. Although we are looking for other different material which is cheaper than the gold, but gold has its own unique chemistry. I skip these details to save the time and go to last. So before going to the last example, so I told you this, the picture of filling the CO2 in your car and then driving the car by the CO2. See here, CO2 plus water, both are free, and the catalyst, black gold, and the light visible to near, sunlight. So except catalyst, everything is free, and I get a methane, right? So you put CO2 in your car, water in your car, and the black gold catalyst, pass through them to this black gold catalytic reactor, expose them with the sunlight, you get a methane, burn the methane, you get the energy, drive the car, and you get the CO2 back, and this will be a cyclic reaction, right? So you can see at a lab scale, it is feasible. The problem is y-axis, the amount of methane yield. It's a 2, it's not 2, even it's 1.5 micromole per gram. It's extremely small. Still, it is far better than the normal gold. So, but in reality, if one really want to use it commercially, these numbers has to be in thousands. You need to produce thousands of micromole per gram. Then this thing is possible. So science is there. You need to have even better fundamental discoveries to get a better catalytic materials, and this may be possible one day, very soon. Okay, the last 5 minutes is about the plastic waste. Not really related to CO2, but you know, plastic waste is another very serious issue that entire world is facing, and definitely India is facing even worse. So we produce large amount of plastic, 26,000 tons of plastic waste every single day, and we don't know what to do with it. And it's not only lying on our land, but it is also in the air. You see this very recent paper in Science where they say that there is a plastic, microplastic in the air, and when the rain falls on planet Earth, they bring that with them. Now, like an acid rain, which was another challenging issue that we had, the plastic rain is another issue now we're facing. And when the microplastic goes into the water, what will happen? The water, those will go into the fish and some other thing, and then you will eat the fish, and that microplastic goes into your body. Some of you will say that, oh, I'm a vegetarian, doesn't care. That's not true. See the next example, where the plastic bottles, if the temperature is between 40 to 60 degrees Celsius, then again the microplastic and other carcinogenic compound leaches out from the plastic bottle to your water. And 40 to 60 degrees Celsius, like I'm from Nagpur, it's 45 degrees Celsius in summer. Maybe several other places in your region also has a high temperature. You can imagine how serious the waste plastic issue is. Now, how do I solve the waste plastic issue? So if you look at the chemistry of the plastic bottle is polyethylene terephthalate. Centrifuge tube is polypropylene. Carry bag is high density polyethylene. So if somehow I break these CC bonds and CO bonds and CH bond and go back to these basic chemicals, alkenes and long chain alkanes, then done, right? I have converted the waste plastic back to the chemicals from where it was formed. So I'm recycling it. But the problem is this needs lots of energy. And that means if I have a carry bag costing 1 rupee, to degrade that I need a 10 rupees. So no one will do that, right? Why will I spend extra 9 rupees to get 1 rupees back? So that's the problem. So there is the issue with the sustainability, and what you need then, you need a catalytic process which allow you to do this at a lower temperature more efficiently, so that I can degrade and convert the plastic into chemicals. And this is what we recently showed, that we developed nano sponges of aluminosilicate, which has acidity very similar to zeolite, but at the same time the porosity very similar to amorphous aluminosilicate. And that allows even the bigger plastic macromolecules to diffuse inside because of the bigger porosity. And now it has a strong acidity, degraded that into various chemicals. We also showed that one can also use the CO2 as a fuel. So this is an example where we showed that plastic can be converted into chemicals by using our nano sponges. And this is the example where we showed that CO2 can be converted into dimethyl ether in one step using copper, zinc, aluminum catalyst, obviously. And because of the strong acidity and porosity, it shows excellent selectivity towards DME. Okay, with that, I like to conclude that I showed you DFNS, a high surface area material, and uniqueness of its morphology. Then I showed you how to create the defects in these DFNS, in these nano silica, and how the cooperativity between the defect able to activate the CO2 and convert them into chemicals, fuels. Then I showed you the way to tune the distances between the gold nanoparticle and make a black gold, which has the ability to absorb light from visible to near IR, and also has the ability to produce lots of heat isolated to the nanoparticle. So that's why we call it cold heating. as well as the hot electrons. And at the last, in the last example, I showed you something amorphous zeolite, which is actually a amorphous aluminosilicate, which has acidity like zeolite, but porosity like amorphous silicate. And the goal of my group at TI from Mumbai is to really come up with a CO2 conversion protocol that work at ambient temperature, ambient pressure, no external energy, and water as a hydrogen source, using inexpensive and abundant material, and with a great productivity, so that I can really solve these 32 gigatons of CO2 issues that we are facing, and hope one day this will be possible. With that, I'd like to thank Department of Atomic Energy, who funds TI for Mumbai, as well as other funding agencies, the Indo-French CEFIPRA, Shell Industries, DST DBT Mission Innovation. And I'd like to thank my group, and Maiti, Rajesh Belkamwar, Rishi Verma, Sushma Kundu, and Sushma Rao. We have a very small group. And I'd like to thank you very much for listening to me. And I hope you must have realized that what we need is a fundamental research, a breakthrough in the fundamental research to really solve the problem of climate change. And obviously, I respect Tohomi Baba for starting one of the greatest institute in the country, that is TI from Mumbai. With that, thank you very much again.
Thank you, sir. That was a wonderful session. Now I'd like to move on to the Q&A session of the webinar. Sir, are you ready? Can I ask the first question?
Yes, go ahead.
Okay, the first question was asked by Sriram Sundar, and the question is, use of nanotechnology in catalyst manufacturing, how significant is it?
Still, nanocatalysis is still at a research scale. I would say there are not many examples of nanomaterials being used in the catalysis, but there are several examples. Like there's a scientist called Graham Hutching in UK. He recently wrote a JAX paper where he showed how the discovery in his lab were commercialized and how beneficial that was by using some of the gold nanoparticles. So one has to take some risk. That is something the industry don't want to. But if we do some risk, there will be some success, some loss. But you can clearly see the dramatic effect of the use of nanomaterials in catalysis. So it's not yet at a commercial scale, but I sincerely, personally hope that it will happen soon.
Thank you, sir. The next question is by Jinsey George, and the question is, which one gives better surface properties, bottom up or top down?
See, surface property, I don't know, that is a broad definition. If you are looking at a surface area as one of the surface property, then it's irrespective of which method you use, it depends on the size. If I use a top down and I get 1 nanometer particle, or if I use a bottom up and I get 1 nanometer particle, the surface area will remain the same, right? So, but if I want to have monodisposed particles of 1 nanometer, then the top down may be difficult. You always get a heterogeneity in the particle size. Whereas when I go to bottom up, I have a control over the way I grow the particles, and I get a monodispersed nanoparticles. About the surface properties as such, let us say if I'm just breaking the gold into smaller particles, I may get a gold 0 and some amount of oxidized gold. Whereas if I'm using a bottom up, I can make sure that my gold nanoparticles are coated with something, or functionalized with something. So there is a possibility of tuning the surface properties or a surface functional group when I use a bottom up approach. So these are the advantage and disadvantage, I will say.
Thank you, sir. The next question is by Sriram Sundar, and the question is, for petroleum refinery, where and how nanotechnology can be applied? Are there such technology in commercial scale? If so, details of the reference installations.
I don't have the reference installation, but there are several examples. Not in India, obviously. India export everything from the state. Although we're collaborating with HPCL and other industry where we're trying to prove that nanoparticles can be used. But otherwise, at this stage, I think it's still not progress in that direction.
Thank you, sir. The next question is by Physics SCT. Sir, do the nanophosphors of rare earth materials have any significant role in this topic?
I have no idea about nanophosphorus. Could be. I think they do harvest the solar light, so one can use them as a photocatalyst or something like that. But I have no idea about the nanophosphorus. I don't work in that area.
Okay, sir. The next question is by Elda Joseph. Can you please tell about nano devices?
Nano devices, again, a very general question. I think any device which uses the nanoparticles can be named as a nano devices, right? So I don't know what you mean by that, but people are using these nanoparticles to build different devices, right? Which will be smaller and still having the same function.
Thank you, sir. The next question is by Sarah John. Does the methane produced by nano harvesters have more fuel efficiency than that produced by nano catalysts? Which method is more useful?
Which one was that? Nano catalyst, and the first one was nano.
Harvesters, sir.
What is nano harvest? It's the same thing, right? Whether it's a nanoparticle, you can call nanoparticles or a nano harvester. The way I understood is if that it's converting CO2 to methane, it's the same thing, right? And if it is a methane, whether you get it from CO2 or whether you get it from naturally occurring sources, it will have the same energy potential, right? That won't change. What is changing is when I use the methane coming from the natural sources and I burn, I produce CO2. Whereas I'm using the waste CO2 to produce methane. So it's a CO2 neutral process. Whereas the other one is a CO2 positive process. So you're putting CO2 in the environment.
Okay, thank you, sir. Next question is by Jeevan Jacob. Is there any technique to remove CO2 at the source while food processing or refining?
Yes, obviously, that's a very good question, and that should be one of the obvious things that all the industries should think of. If they don't allow any CO2 to go out, the CO2 problem is solved, right? So this is called the CO2 capture. CO2 capture at source. Then there are two types. One is at a lower temperature, the CO2 that is coming from your chimney, which is say around 75 degrees Celsius, or cool down to 75 degrees Celsius and capture that. Other one is while during the reaction, let us say I'm doing some hydrogen production from some fossil fuel and producing the CO2. So I capture the CO2 during the reaction at that high temperature. So there is a higher temperature CO2 capture. So there are processes which does allow this to happen. The room temperature or low temperature CO2 capture process are commercialized now. There are lots of industry who does the CO2 capture. The high temperature is still at a research level.
Okay, thank you, sir. The next question is, what is the reason for the expansion of ozone hole during 2020?
I have no idea about that, but I don't think that it has anything to do with CO2. I think that's a chlorofluorocarbon, right? That's one of the reasons for ozone hole to deplete. But otherwise, I don't really know what happened that year.
Okay, sir. Is there any bacteria exist that dissolve plastic?
Yeah, there was a recent result from Japan where they developed some bacteria which eats the plastic. So there are some results there.
Okay, Anju Ji has asked, can microplastic dissolve in our bloodstream?
I really don't know, but ideally plastics are very unreactive, and I don't think our blood is so acidic that it will dissolve the plastic. So I don't personally think, but I'm not expert in this. So you have to ask some biologist. But I personally feel that it may be very difficult.
Okay, Reena Joshi has asked, can we degrade plastic using nano catalyst?
Yes, that's what I showed you at the end, that you can degrade the plastic using the nano catalyst, and you can do that at a very low temperature, and that's the objective of the project. So you degrade in the sense you convert the plastic waste into some useful chemicals, right? You just don't degrade, but convert into some useful chemicals, and that is possible.
Thank you, sir. The next question is by Alicia Lewis. Sir, how nanotechnology be applied as an effective tool for enhancing bioavailability and bioactivity of medicines?
I don't have the slide, but there are nowadays recent results where people are using nanoparticles as a drug delivery agent. So you need a less amount of drug because now your efficiency is delivery efficiency is more. Even nanoparticle itself can act as a drug. It can be used in the sensing, diagnostic, as well as in treatment of the disease. I generally show some slide, but today it was more about the CO2, so I did not show it. But there are examples, there are studies where people are using nanoparticles in medicinal chemistry.
Okay, thank you, sir. Sohan Goswami has asked, how much can it take actually to implement this in automobiles?
Pardon, can you repeat the question?
Yes, sir. Uh, how much can it take actually to implement this in automobiles?
Okay, so the thing I told you about running the automobiles using the CO2, right? So the results are there in the lab scale, but the problem is the productivity. If I want to convert CO2 to methane, I need to really convert large amount of CO2, maybe liters of the CO2 into liters of the methane, let's say in few minutes of time. That is not happening. That rate of a reaction is really low. So once we develop a catalyst which has a higher rate of a reaction, then ideally there is nothing to stop. There is nothing to stop. So it's just a fundamental breakthrough that one is needed, where I develop a nano catalyst or a catalyst which will have a higher reaction rate.
Okay, sir. Elder Joseph has asked, risks of nanoparticles to human health.
Yes, that's very valid question because they are very small. They can penetrate into your membranes, into your cells, and they may affect your health. And this is something every time if you want to commercialize something, you must do a biosafety of those nanoparticles. There are some nanoparticles which are very safe, like silica. People are using silica as a drug delivery agent, so we know that it is safe. But there are other nanoparticles which are not safe. So that is another thing that we all look for, using safer metals, non-toxic metals, something like that.
Thank you. Rohitas Prasad has asked, by what order of magnitude does the kinetics of catalysis vary in nanoparticle and macroscale particle of the same material? Can standard kinetic equations be applied in this case as well?
Yes, the standard kinetic equation will be applied. The science is not changing; it's only the rate which is changing, and there cannot be a direct answer because it depends on which metal and which reaction you are talking about. But there is a dramatic change, really dramatic change. I need to show you some data about the bulk versus nano, but for right now, you can take it's huge. Maybe sometime 10 times, maybe 100 times, maybe 1,000 times, even more than that. So that depends upon the nanoparticle as well as the reaction. The same nanomaterial can be very reactive for some reaction, can be less reactive for some reaction. So it's very specific to the reaction and the metal nanoparticle that we are referring to.
Thank you, sir. Devi Priya has asked, how far have we progressed when it comes to using nanotech in the case of oil spills?
In case of?
Oil spills. Oil spills.
Oil spills. Yeah, there are, I don't know, oil spills. There are research in the field of nanoparticle, but there are also research in the field of polymer science, where people are developing different porous polymer and they do absorb lots of oils. So I think that is a better way rather than using a nanoparticle and spreading them into the water.
I guess the questions are over, sir.
Okay.
Thank you, sir. That was such an informative talk. I thank you on the behalf of the Department of Biotechnology and Biochemical Engineering of Sri Chitrathana College of Engineering, Trivandrum. I also express my sincere gratitude on the behalf of all the participants attending the webinar. Thank you very much, sir.
Thank you very much. Thank you, everyone.
Thank you, Dr. Vivek. Thank you so much.
Thank you, Dr. Vivek. Thank you.
Yeah, thank you.
Okay. Bye-bye.
Bye.
Yes, sir. Now to the participants, I request all of you to fill the feedback form which is displayed in the chat box for the availability of the e-certificates. Kindly do it as fast as possible. Thank you once again.
Hello.
Hello. Hello.
Sir, good evening, Sriram.